Okay, this video is going to look at something called Snell's law, which is an extension of the stuff we've been doing so far on refraction. Now you remember from last time that refraction is how light bends as it moves from one optical medium into another if the speed of light is different in that new optical medium. So for example, if something passes from air into water, the speed of light in water is less, so it will slow down, and as it slows down, it will be refracted or bent as it passes through. So this diagram here in the top right-hand corner shows a light ray passing from air into a block of plastic or glass and being refracted, bent inwards, and then as it passes back out from the plastic into the air again, it's bent outwards. So in this video, we're going to take that idea and extend it beyond just purely descriptive language to actually come up with a thing called Snell's law, which is a mathematical angle that allows us to calculate the angles of incidence and the angles of refraction. So Snell's law is named after a Dutch guy called Willebrord Snell, and he discovered it in 1621, so almost 400 years ago. Now, although I probably should say for fairness here that this law had already been discovered hundreds of years earlier by a guy called Ibn Sahl, who was a Persian working in Iraq, I think. So you might say to yourself, well, why isn't it called Sahl's law instead of Willebrord's law? Snell's law? Well, it's basically because a lot of science was done by Islamic scholars in that time, around about the 900s, but there was no communication between Europe and between the Middle East. At the time, Europe was in the Dark Ages, so it was just full of rampaging yobbos, basically, guys with swords killing people. It wasn't until much later that Europe sort of became civilized, like the Middle East was at that time, and they sort of rediscovered a lot of science for themselves. So Ibn Sahl came up with the idea of Snell's law before Snell did, but because there was no sort of communication between scientists in the Middle East and scientists in Europe, no one knew about that in Europe. Anyway, so let's start off by looking at another idea called Fermat's principle of least time. So this was discovered by a mathematician, a French guy called Pierre de Fermat. The T is silent. That's him there in the top right-hand corner. So famous mathematician, and from the looks of it, lover of pie as well, I'd say. Bit chubby. But he basically discovered this. He just was able to discover that light, when traveling from one point A to another point B, will always choose, now you'll see I've put that in commas, will always choose the path that takes the least amount of total time. Now when I say choose, it doesn't mean that the light has magical properties and can think for itself and it can somehow pick the right path to take, but it behaves as though it can. So a light ray will always go in a path that gets it from point A to point B in the least amount of time. So I've got a little video here showing what's going on. And now in this video, I've basically set up an animation in GeoGebra. I've got 2 points A and B. A is in air, B is in water. And then I've got a point C that I can move backwards and forwards to look at different paths that the light can take. Now remember, the light has to travel in straight lines, and the only way it can change its movement is that the straight lines can bend as the light ray goes from air into water. So I can move this point C backwards and forwards. And then over here, I've set up a little calculation here so I can work out, firstly, the time it takes to get from A to C, which is called time AC. And then after that, the time it takes to get from C to B, which is time CB. And then I've added those two together to create the total time. And what I'm trying to do here is I'm trying to look for the position where that total time will be as small as I can get it, the least amount of time, and that will be the actual path that the light ray takes. So you can see as I move this backwards and forwards, there'll be one spot where the number is smaller than any of the other spots. Now it's not the direct path, which you can see here. Oh, let me rewind that a little bit. So it's not that path there, that's the direct path that goes in a straight line from A to B. You might think that's the quickest route. It's the route that has the least amount of distance. But if you think about it, we know that the light ray is going to travel slower in water. And at this particular angle here, it has to travel through a lot of water. So even though it travels fast through the air, it'll travel a lot slower in the water. So this straight line won't necessarily be the best position. The best position is going to be one where it travels a fair distance through the air, because that's faster, and then a little distance through the water. It's about finding that balance. So if we go back to the video now, I'm dragging this little point C backwards and forwards. I'm trying to get that total time number to be as small as I possibly can. And I get to that point about there where I am now. So the smallest amount of time I can get is 11.61, which is about there. So that there is the actual path that the light ray will take. It won't go in a straight line from A to B. It'll go from A to C, and then it'll bend inwards, be refracted inwards, and go from C to B. And that path will take the least amount of time to get from A to B. Okay, so I've taken this and I've added some extra stuff into there. I've measured two angles here, the angle of incidence here, 43.5 degrees, and the angle of refraction here, 31.2 degrees. So you can see this light is bending inwards, which we'd expect because it's going from a lower refractive index to a higher one. And we know that when that happens, light gets refracted inwards. Now over here, I've put in two calculations. The first one, Ni, you might remember stands for the refractive index in the incident material, so where it's coming from. So it's coming from air, so the Ni would be the refractive index of air, which is just 1. And then over here, I'm timesing that by the sine of theta I, the angle of incidence. So I'm timesing it by the sine of 43.5 degrees at the moment, okay? And then when I times those two together, I get 0.69. And then I can do the same thing for the bottom. So you can see at this position here, Ni times sine theta I and Nr times sine theta R are both equal to 0.69, so they're equal to each other basically. So that's at that sweet spot we found, the point of least time. Now if we were to take that and move it to different positions, we'll see that it's no longer equal at other positions. So that point we were at before, the point that takes the least amount of time, which is the actual path that the light ray takes, that'll be the point where those two things are equal. So that's the point we want there. At that point, which is the path we know that light ray actually takes, Ni sine theta I and Nr sine theta R will be equal. They'll both be equal to 0.69. So that brings us on to Snell's law. Okay, so this is Snell's law here down the bottom. Ni, the refractive index in the incident material, times sine of theta I, where theta I is the angle of incidence, is equal to Nr, which is the refractive index in the refracted material, times the sine of theta R, where theta R is the angle of refraction. Those two things will always be equal for a light ray that's passing from one material into another. So if we know that formula, we can then work out things like the angle of incidence and the angle of refraction if we're given other information. So in this little diagram here to the right, I've just kind of illustrated what I'm talking about. So Ni is the refractive index for the incident material it's coming from. Theta I is the angle of incidence there, measured around the normal, as we talked about before. And then theta R is the angle of refraction, and Nr is the refractive index of the material it's passing into. So we've used I for anything that has to do with incident side, and R for anything that has to do with the refracted side of the boundary. And the other thing you have to remember as well is just to make sure that when you do this, your calculator is set to degrees and not to radians. Now, you probably haven't looked at radians yet in maths. Radians is an alternative way of measuring angles instead of degrees. It's used in like advanced year 11 maths and year 12 maths. All you need to know is don't set your calculator to radians, and if you keep getting the wrong answer, it's probably accidentally been set to radians. The way you can normally tell is you look up the top of your calculator screen. If you can see a little tiny d somewhere, it means it's set to degrees and you're all good. If you can see a little r somewhere, it's set to radians and you might have a problem. So that's just a little check. If you keep doing the right thing, but you get the wrong answer all the time, maybe you've got your calculator set up wrong. It needs to be in degrees and not radians. Okay, so that was just a basic introduction to Snell's law and what it is. The next video in this series actually looks at problem solving with Snell's law. So it looks at 3 problems involving Snell's law and how to solve them. Okay, so I suggest you now go on and watch that second video.